So here's a little bit of classroom overtime, or maybe classroom replacement, since we're not meeting today on Wednesday right before fall break. We need to see some examples of the use of the exponential growth and decay formula. And so here you go. You have 2 handouts left over from class that have these problems on them. These particular examples here, I'm not writing on the handout because I needed a little bit more space. So the first problem we're going to take a look at is your very traditional exponential growth problem for bacteria. The exponential growth formula that we would like to use is this one in this problem and any other problem involving exponential growth. Here we have a bacteria culture with 100 cells in it. It's going to start growing, and somebody's measured that after an hour the population has increased to 420. We need the magic numbers P0 and K in order to make this equation work and produce new results. We are given P0, that's the initial population of 100. We need to know K. K isn't given. We're not told, hey, the growth rate is this. But this extra data point that we have allows us to back it out. So we're not given K directly, but we're given data to discover K. And by that, I mean there are 4 places in this formula where numbers can go. As long as you're given any 3 of them, you can discover the 4th. And so we're told that if we start with 100 cells and let 1 hour go by, we will end up with 420 cells. And the only unknown here is K. So this tells us that 4.2 equals e to the k, or the natural log of 4.2 equals k. And we'll leave it as natural log of 4.2. You could get a decimalized version of that. And so in the handout, the first actual question says find an expression for the number of bacteria after t hours. Well, we've just produced the magic numbers to fill this in as specific to this case, and that is the population of this culture after so many hours, having started at 100 and a growth rate of 4.2. This formula here will now tell us everything. So from this point on, we can be given a time and calculate the population after that time, or we could be given a target population and ask for the time it took to get there. This routine is going to be identical no matter what the context is. If the context is totally different from this, but you're still going to use the same exponential growth or decay formula, it usually starts off exactly the same way. If you're not given K directly, you're going to be given enough information to figure out K. And no matter what other questions there are, this is the first thing you need to do, is discover your growth rate. Here are the second 2 questions on your handout about this problem. I've rewritten the equation that we just discovered or completed, and now we're ready to use it over and over again. The specific question at hand is to find the number of bacteria after 3 hours. This is literally as plug and chug as you can get. So with an initial population of 100 and the growth rate we have now figured out on the previous page, we learn that after 3 hours, we will get, well, whatever population is there after 3 hours. And I don't actually have this number, so punch some buttons in your calculator if you like. You know, clearly it'll be bigger than 100, right? Because the population is growing. But just take 3 times a natural log of 4.2, figure out e to that number, multiply it by 100, and you'll get that answer. You'll get that value. It's a direct calculation. The flip side, when will the population reach 10,000? Well, if we set up the same structure, P equals P0 e to the kt, remember again that we've already discovered the growth constant of natural log of 4.2. We already know that this population started with 100. So unlike the question above, where we were given t and asked to calculate p, here we're saying, hey, we want the population to reach 10,000, and we go to the equation and we say, hey, equation, at what value of t will our population reach 10,000? And so now we have to solve for t. It's still simple, it's just we have to algebraically solve for it. It's not just a direct calculation like the one above. So starting to solve for t, let's divide by 100, and that will leave 100 on the left-hand side, e to the natural log of 4.2 times t. Since we need to solve for a variable that's buried up in the exponent, we have to take natural logs of both sides. So natural log of, whoops, I guess it would help if I put that equal sign in there, wouldn't it, right? That equal sign is that equal sign. And now we're taking the natural log of both sides of this equation. It's a little gross looking because now we have two different natural logs in play, but the benefit of this one is now that the natural log and the e being inverses of each other do the elimination thing, and we have the natural log of 100 equals natural log of 4.2 times t, and so t is the natural log of 100 over the natural log of 4.2. And again, whatever number that turns out to be, that's how many hours it takes to reach the population of 10,000. The second problem on your first handout from yesterday, or from Monday, is an exponential decay problem. Radioactive decay, cesium-137, has a half-life of 30 years, and we start with 100 milligrams, and we're going to go from there. The first thing you're asked to do is to derive the function that drives all of this. It's the exponential growth or decay function. Because we're dealing with exponential decay, we're going to have e to the negative kt, so we have decay instead of growth. And just for clarity, I've changed the variable, the dependent variable, from p for population to a for amount. Right? It's the same structure. The letters in it don't really matter much. Right? So we're going to have to do exactly the same thing as we did in the previous problem, which is discover k. So we're not told the decay rate. We're told an initial amount of 100, so 100 is going to be a 0 throughout the whole problem. And we're told the half-life is 30 years. What that tells us is that after 30 years, the amount's going to drop to 50, right? So kind of like in the previous problem, I can leave some boxes for the 4 numbers that could go into this. That minus sign is not a blank. That's the negative in the exponent. So we have a starting amount of 100. We are told that after 30 years, whatever amount is there will have decayed to half what it started with. That's what the half-life is. So after 30 years, we'll be down to 50 milligrams. And so now, here I'll even put it in a different color just to make it exciting. Now we can solve for our decay constant, k. Dividing by 100, we will get 100 equals e to the negative 30 k. And look at what happened here. We started with 100. Half-life means that drops to 50. If we'd started with 200, half-life, it would drop to 100. But no matter what you start with, as soon as you do that division, the initial amount and half the initial amount is going to cancel out to 1/2. Half-life is the half-life, and it doesn't relate to the starting amount. So even if we were not told we started with 100 milligrams, we would just say cesium-137 has a half-life of 30 years. What is its decay constant? Even without being told an initial amount, we could just say put 1 here and 1/2 here, right? And then we would decay from 1 to half that amount in 30 years, and we could still get the decay constant, because this starting line will always produce this one as long as you're talking about half-life. That was a diversion. We're still solving for k. It's up in the exponent. We need to take natural logs. And I'm going to take a shortcut. When I take the natural log of the right-hand side, we'll just get the negative 30k directly. And so now we can solve for k. It's negative, the natural log of 1/2 over negative 30. Remember that the natural log of 1/2 is minus the natural log of 2. And so we can write natural log of 2 over 30 as the half-life. Sorry, as the decay constant. Or you could leave it like this, but that's more cluttered. You could also, again, punch this into a calculator and get the decimalized version of it. So the governing function, well, darn it, I've run out of room in this space. That's the danger of prepping these sheets ahead of time. So I'm going to just construct the function in the next line with a starting amount of 100 milligrams. We plug in the decay rate that we just discovered, and now we have the function that will drive everything. We have an initial amount, we have a decay constant, and now we can get pairs of time and amount in any configuration we want. We can be given a time and discover the amount, as in question B, or we can be given a target amount and have to decide how long it takes to get there, as in question C. In question B, we're asked how much remains after 100 years. Well, we're just going to plug in 100 for t, right? So 100 e to the negative natural log of 2 over 30 for the k times 100. Oops, and it ran off the screen just a little bit there. And again, this is button pushy, so just get out a calculator and punch, 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 get those numbers. It'll be what it is. I'll tell you what I'm going to do is when I'm done making this video, I'm going to take all of my pages that I've written. I'm going to go back and I'm actually going to calculate the final numbers and put them on the sheets, and then I'll scan the sheets. And so you'll have the video as well as scanned versions of the final sheets with all those final numbers so that you can check your own work against those values. With this same governing function, how long until only 1 milligram remains? Well, there we're given a target amount of 1 milligram, having started with 100, with a decay rate of natural log of 2 over 30. And now we're going to ask for t. We're going to solve for how long it takes to make this happen. So we have, running out of space, 1 over 100 equals e to the negative natural log of 2 over 30 t. Going to take the natural log of both sides. I'm squeezing this in. So imagine I've taken, here, I'll do it in a different color just so it, how about light blue? This will be exciting. All right, going to take the natural log of both sides. The natural log of 1 over 100 is negative natural log of 100. I would rather write a negative natural log of an integer than a positive natural log of a fraction. So I'm changing log of 1 over 100 into negative log of 100. Over on this side, that natural log and that e do their thing and get rid of each other. And so then we're left with negative natural log of 2 over 30 times t. Or t equals 30 times natural log of 100 over natural log of 2. And if you want button pushing, go do button pushing.